Good afternoon all. Welcome to the IMarEST TV session for today. Today we've got Jennifer here who's going to talk to us about turbine technologies for the Tidal. Jennifer has been with the Offshore Renewable Special Interest Group for a few years now, and she's championing the early career as well. So,
thank you,
Jennifer.
Okay, thank you everyone. Good afternoon. My name is Jennifer Molina, and I'm a project manager for VerdErg Renewable Energy. VerdErg are developing the Venturi-Enhanced Turbine Technology, or VETT for short, which is what I'll be talking about today. So, the idea of VETT came from an existing application in Naval Architecture. So I'm going to talk about how we took that inspiration and developed VETT. We'll also cover the basic principles and applications of the technology, the results from our latest fish trials, and also what progress we've made with run-of-river projects. As this is a marine audience and you love all things marine, I'll also cover the work and our ambition for the tidal market. VerdErg. Well, VerdErg was established in 1979, and it comes from a subsea hardware supply service background with clients all over the world, projects all over the world. They have experience in developing infrastructure and connectors, and so our design team have this experience and they apply this experience to the development of VETT, and in particular the robust and reliability that you need in developing in harsh marine environments. And that's really important, obviously, for marine renewables. So the company, when it was set up, it had a management buyout in 2005, and to focus on deep water diverless connections for the oil and gas industry. And it grew from 30 people to about 140, and then in 2014, the subsea hardware side of the business was sold, so that the company could focus as VerdErg Renewable Energy exclusively on hydropower and on developing VETT. So what is VETT? Well, VETT essentially is a low-head hydropower device, and it generates power from fluvial flows with a 1 to 3 meter head drop. And it takes this fluvial flow and it amplifies the pressure that the turbine would see. So conventional technology, in order to generate power from these fluvial flows, they have to use large machinery, which can be expensive and quite a task to install. However, because of this pressure amplification, we're able to use a smaller high-speed turbine, which has a much smaller civil footprint and environmental impact. Where other technologies may prioritize efficiency, we also prioritize the cost of energy. So that's what makes us different. How does it work? It uses the amplification of pressure that a turbine would see. So 20% of the flow is passed through the turbine, and then the remaining 80% of the flow goes through constriction. So the turbine sees an amplified pressure from the intake to where it is discharged into the constriction, into the Venturi. So in a typical site with a 2 meter driving head, instead of seeing 2 meters, it now sees 6 meters. And that is just using a fifth of the volumetric flow. So because of this, you can use a smaller turbine, and that is fantastic because it's obviously cheaper and much easier to install. So where did the idea come from? 2 people, really. Firstly, Daniel Bernouli in 1738, with his principle, his Venturi principle, which is when kinetic energy in fluid, when it increases, so when the velocity increases, the pressure simultaneously decreases. The other person was Mr. Peter Roberts, who is the managing director of VerdErg Renewable Energy, but also the inventor of the technology. So he came across the application of Venturis when designing eductors to pump ballast water from flooded compartments. So for those of you who are not familiar with eductors, or indeed 18th century hydrodynamic principles, eductors basically pump a high jet of water through a nozzle, and then behind that nozzle you have an area of low pressure causing suction. A suction hose is connected to that, and that entrains another flow. VETT basically acts in the same way. It takes the 80% of the flow and passes it through a constriction, and then the secondary turbine flow is sucked in into the Venturi. These two flows are then mixed, and then they diffuse further downstream. So currently we are very busy developing VETT for river applications. We're doing our commercial demonstrator at the moment and have various other in the pipeline. But we also have done some work taking VETT for tidal applications, which I'll cover a bit later. We've also got our eyes set on wave energy, but a little at a time. I realise you can't do all this innovation all at the same time. So we'll get there. So to get where we are, we have done so many numerical models, computational models, laboratory and field tests, and that's generated 6 patents and counting. Key milestones from all of this include the first principles of VETT being audited by Atkins in 2009, and then our successful live fish trials, which we did in 2013 and 16. Also generating first power in 2014, but most recently we had approval from the Environment Agency to install for run-of-river hydropower. So looking back to our prototypes and field testing, we took our VETT technology and installed a full-scale, fully instrumented test rig at the BHR Group Test Facility in Cranfield, based on the Cranfield University campus. So this test rig was testing head drops of up to 3 meters, and here you can see, I can't point for this, but the tank simulates downstream, so that is the downstream, and the VETT is made out of perspex, and that is in the middle. So here we wanted to just analyze the hydrodynamic performance of VETT, and we wanted to see if we could recreate that in the field. So we took the whole test rig and installed it in a river up in Cumbria on a spillway. So here you see the spillway as it was, and then we have a schematic of the test rig as we had intended. There is a header tank to take the water in upstream, pass it through the VETT and discharge it into a sink tank downstream. And on the right you will see an image of what the test rig looked like. And of course, as is always the way, we installed in midwinter. You planned for summer, but because of weather and lead times, I was dressed as an Eskimo for most of that testing program. But this was fantastic, and we were really pleased because we managed to prove that we could replicate the hydrodynamic performance and power output that we did in the lab in the field, and that was certified and verified by Lloyd's Register. So, taking that linear device, VETT, which takes the turbine flow and introduces it into the Venturi from the sides, Peter designed another version where the turbine flow goes through the middle, and this is the coaxial version. This again is in the VHR lab, so there you can see the header tank simulating upstream, and then the VETT made out of stainless steel, and the mixing section, which is where the Venturi is, that is made out of perspex, so we can see the behaviour and nature of the flows. This again was fully instrumented. What was key here, not only in assessing the new configuration, but also it was the first time that we connected the test rig to a turbine and generator. So before we had simulated power and inferred power using orifice plates, and now we had connected it to a turbine and we generated power, as beautifully exhibited by these showbiz lights, which was great fun. They're actually car lights, so it's great working with engineers because they find such ingenious ways of incorporating existing kit. So this is what the coaxial VETT looks like. As you can see, the 20% of the flow goes through the turbine and the turbine shaft there, and then the 80% of the flow goes around the outside. The Venturi, as you see, it kind of constricts in the middle and then it diffuses further down. But testing VETT and evaluating its performance hasn't all been test rigs and toys. We've also done lots of computational fluid dynamic models. This time we worked with Arup's Advanced Technology and Research team. So they created a model to assess the hydrodynamic nature within VETT and how we could find design improvements and performance enhancements. We had tried this before, but there just wasn't the software or computational power to really recreate and capture VETT accurately. So this is the first time that we could do that. What was great about this program was that we could take the data from the physical trials and validate this model. So there we were able to really recreate VETT, and then from there come up with new design iterations and performance enhancements without having to go back in the lab. Although lab testing is really great fun, it is quite costly, so this is a really good tool for us. What would a VETT look like? Well, this is for river schemes. So here we're using VETT to generate power from the head difference across an existing weir, which you can see in the top right. Here on the left you can see a manhole chamber, which obviously for maintenance, and then the intake chamber, which is what VETT sits in. And in front of that you have a debris screen. So the intake chamber is submerged, and further downstream you can see a fish pass. Given the existing environmental legislation and Water Framework Directive, it's important to have river connectivity, so fish passes are important to help our fisheries access the upstream nursery and feeding grounds. What's important to take away here is the visual impact. The header tank is submerged and there is minimal visual impact, which is really important for designated areas, designated for environmental amenity, but also in heritage areas as well. Looking inside the tank, we have a sluice gate which you can use to shut off the whole system for maintenance. We also have the turbine, which could be submerged or dry enclosed, and the fish screen goes just across the turbine. This screen also helps direct the 80% of the flow to go through the VETT, and that VETT connects to a downstream pipe which discharges the flow downstream of the weir. What's important to note here is that the fish screen only covers the turbine, which reduces the extent of maintenance, because existing hydropower devices normally have to screen the whole of the intake. So that's a massive cost saving there. So, sites that we're looking at, in addition to weirs, we're also looking at lock structures and spillways, and anywhere where really there's a 1 to 3 metre head drop. And we're looking potentially at generating between 30 and 100 kilowatts. Although not very much, every little bit helps, especially given the energy targets and renewable energy targets that we have set for the UK. So that's the environment, the engineering side, and the hydrodynamics and performance validated. What about the environmental design criteria? For a renewable energy device to be truly green, we've got to think about what ecosystem it goes in and the species that reside there. So for hydropower, that's basically fish, and fish is the key part of that, in addition to the invertebrates and aquatic fauna, but fish are directly impacted by the turbines. So we wanted to assess fish survivability in the second phase of testing and look at 4 particular impacts. So one was the impact of the higher pressure ratio that occurs in the VETT. So there's a massive pressure flux, and fish have swim bladders which are sometimes susceptible to pressure fluxes. So we wanted to look at the impact of that. We also wanted to look at the impact of different fish species. So we tested salmon and eel and lamprey and bream. As fish occur at different areas in the water column, we also wanted to look at the effect of depth acclimatization and also post-passage swim behaviour. So this test rig was testing with head drops up to 3.5 metres and up to 500 litres per second. So how did the fish cope? How were they with that? So this test rig was installed in HR Wallingford's Food Modelling Hall, and thanks to their really amazing support staff and facilities, we were able to recreate a flow circulation system to simulate a river environment using the sump tanks that they have. So here is an image of what we did. So right across the front you can see the flow circulation pipe leading to the sump tank. Then you can see the Coaxial VETT stainless steel section. The acclimatization chamber, which is where we depth acclimatize the fish, is located up there in the top right. And then the sink tank, which is downstream, is located on the left. Also you can see lots of important people acting very importantly. So looking a bit closer, here we've got the acclimatization tank, and we put fish in there for up to an hour to get them up to either surface or up to 3 meters depth acclimatization. We did that by using a pressure tube, and then they were released into the VETT using a ball valve. And then on the right hand side you will see the image of where the fish came into, so the VETT and then the Venturi section is seen in perspex in the middle. Here we were getting flows of up to 12 meters per second in the Venturi, so they were subjected to, I call it a power shower, but yeah, quite an extreme flow, but you'll see how it all went. We also set up the fish holding area around the back of the test hall, and fish husbandry and sourcing the test fish and doing the analysis of the fish was conducted by Fish Tech, who are a consultancy who specialise in this thing. And they were fantastic. They really helped us understand the nature of the impact on fish and did all of our reporting. As you can see, they're hanging over the edge looking at the post-passage swim behaviour of the fish. Also not only within the tank immediately, but we also monitor them for 48 hours post-passage. And you can see the eels swimming in the tube post-passage. So we also did a long-term monitoring to see the impacts of any swim bladder and what repair took place. Fish Tech also managed the dissections and assessed all the internal and external injuries. Results, it all went fabulously, which we're really delighted. There were no mortalities attributed to VETT, which was really, really positive, and that is especially poignant for eel and lamprey, who are protected species. And there was no impact to salmon either, and green. Now perch, who are more susceptible to barotrauma and the pressure fluxes occurring within the technology, they were more vulnerable to the pressure changes. And although they didn't die, they had some swim bladder damage. But when we monitored them after 2 weeks, we found the vast majority had managed to repair their swim bladder. And this is new research, and Fish Tech were really pleased to discover this. So taking that post-passage long-term monitoring into account, the proportion of fish that would go through the VETT in a river, it was calculated that their successful scheme passage rate would be still above 99%. We presented all this research, all the photos of the reports, all the statistical calculations to the Environment Agency, who are in charge of awarding licenses to hydropower schemes in rivers, and they have approved us to install for run-of-river projects. What's really important is they have approved us to install with screening of just the turbine. So we were never going to put fish through the turbine, but we wanted to put them through the Venturi and the main flow. And now that that has been successfully proven, we can now really offer the hydropower market a more cost-effective hydropower solution. So the rest of the turbine screen will now be screened as per the guidance, which is already in place. And once we have a few schemes behind our belt, it will be incorporated into the guidance. So this is a great success for us, and we're very pleased. So that's run-of-river hydro. What about the fun stuff? What about offshore tidal potential? Well, here is a picture of the world, as you can see. And in the dark bits is where there is the most tidal resource. But we're also interested in the grey bits, so where there is between 2 to 4 meter tidal ranges as well, because VETT can generate power from there too. So what have we done to do this? In 2015 we were awarded part funding from Innovate UK, and they helped us look how we could take the basic principles of our unidirectional VETT device and apply it to a bidirectional tidal device. So to do this, we worked with Arup and Brent Measurement Technology to create models of concepts and full assemblies. and this was fantastic. It involved a lot of head scratching, but it was able to help us address this need to address this power potential that we have in the UK. So the CFD models were used to assess not only their hydrodynamic efficiency and the nature, but also how we could improve it and look into other aspects too. Here are some images from the full assemblies that we are looking to take forward. In addition to all the schematics and models we came up with, we also have a lot of report and data files which we use to try and infer more design changes. What's interesting here is how we manipulated the primary flow, the majority 80% flow, and the 20% turbine flow, putting it laterally or on top of each other. It was quite fun and definitely a very innovative phase. On top you can see these large flaps. These are inflatable weirs which can be used to hold back the water and generate the head difference which is required to generate the power. Looking at one concept in particular, full assembly C2, here we've got the turbine flow and the primary flow in parallel. So the turbine flow is introduced from the side into the Venturi on the flood tide, and on the ebb tide we use baffles to sort of redirect the flow, again coming in the opposite direction. What was interesting here is that although 2 turbines are needed, we looked into the prospect of just using 1 generator. So that's all money saving. So it was just not only thinking about design but also thinking about cost and buildability as well. One thing we did come away with was how to incorporate existing equipment and existing technologies. So here we've got an aqua dam, which is basically an inflatable gland, and they come in, I thought in meters of up to 60 meters, in lengths of up to 60 meters, but I found out this morning they come into lengths of up to 100. And they are very easy to install, much easier than conventional barrage technologies where you've got hard infrastructure, which is quite intensive and expensive. Here you've got something that you can install quickly, easily, but also deflate for navigational or flood alleviation purposes. So that was really positive and something we're looking to adopt perhaps in the future. So that's the design, but what about buildability? All these tidal schemes are going to cost money, and so we wanted to see how we could really not only produce the design but also how we could build it in the most cost-effective way possible, incorporating existing installation techniques and construction methodologies. So we looked at possible reef options and what the lead time was on all of this, but much more work is needed, so we're looking to address this in the future. Our next plan for our tidal scheme is to obviously do a prototype. We really love getting out there and just putting the kit in the water. It is really great fun, and it's really worthwhile seeing your drawings go from drawings and sketches on the computer to having equipment built and putting it in and putting all the instrumentation on it, which is really good. So here's a dock site that we were looking at Barrow, and here you can see it fully when the tide is in and when the tide is out. That is a prospect that we're looking to develop in the future. So, as you know, the UK has a fantastic tidal resource. We have apparently 50% of the tidal potential in Europe and the second highest tidal range in the whole wide world, which is really, really fantastic. So, because of VETT's environmental credentials and attractive cost of energy, we've been selected as a candidate technology for the Wild Tidal Energy, who are developing or looking to develop a scheme across the Wyre Estuary. The same also for Solway Energy Gateway, who are developing a scheme across the Solway Firth. Going a bit further afield, the Protype Consortium considered VETT in their best available techniques review, looking at ultra-low head tidal and river power. So we're getting our name out there, which is really positive, but it's really a matter of understanding what's out there and what the issues are and what the potential is, and working with people who want to bring that forward. But doing this is difficult. Tidal, as we've learnt from other projects, just on our doorstep, this is a picture, the top one is a picture of the Solway crossing, which collapsed I think over 100 years ago because of ice flows. There are always problems and issues that we need to account for. But the Henry report, which was published at the end of last year, is encouraging the government to really get behind the tidal industry to exploit our tidal protection. So in light of that, here is just an outline design of what we have planned for the Solway, with an installed capacity of 160 megawatts and an annual energy output of 245 gigawatt hours. Although other technologies may generate more power, we really prioritise the cost of energy. So we look to generate 3/4 of the power for half of the cost and a fraction of the environmental impact. Just this week, I came back yesterday, I was at the Institute of Fisheries Management conference on hydropower and fisheries. And there it is clear, in spite of all the surveys and desk-based studies and site appraisals and models, there's still a lot to be done on understanding the impact of tidal power on the environment. One key issue is the impoundment of water and what impact that has on the hydrodynamic regime. So in 2009, we were awarded funding by DEC, as they were previously known, to take part in the 7 embryonic technology scheme. So basically, technologies that weren't quite ready at the time, but could have the potential in the future to be a candidate solution. So one thing we did was to model the hydrodynamic regime of what the 7 estuary would look like with the VETT installed. So the blue signal is the ocean side and the green signal is the lagoon side. And as you can see, the signal is largely preserved. The amplitude is slightly reduced because you're taking energy out of the system to generate power. So that is the driving head. And there's a slight phase shift because you're taking the flow, 20% of the flow to go through the turbine. But as the scheme is non-consumptive, it rejoins and mixes with the primary flow later on. So there is a bit of a phase shift. But all in all, the barrage, the tidal signal is largely preserved, and that's really, really important for the aquatic ecosystem and the species that are sensitive to it and reliant on it. There's still a lot of work to do, but we'll get there. So here we have a hydropower technology that adopts knowledge transfer and lessons learned from naval architecture and engineering. It also encompasses aquatic and marine science, and we now have this technology which we hope to take to the global marketplace and really make a difference. But building all of this stuff comes at a cost, and thankfully, due to the smaller turbines that VETT can use and the less civil infrastructure and screening of just only the turbine flow, this cost is massively reduced. So we have a lower cost of energy driven by its lower cost of installation. Here at IMarEST, I know they've been great and they're really helping the industry to drive forward innovation so that we can have a positive future, positive energy future. And I really believe that can be a part of that. Thank you for listening.